Hi, I'm Becky Stern, and today we're learning how to pick the best microcontroller for your project. The brain of your project can take many forms, and it can be overwhelming to try to pick one from the vast selection available. I'm going to show you how to navigate the process, including the trade-offs you'll have to make along the way. Identify your project's key features, inputs, and outputs to determine your requirements related to voltage, current draw, communication protocols, number of pins you need to connect everything, the processor speed, and the overall size of your project. If any of those terms are new to you, I suggest you revisit a few previous episodes in this series introducing Arduino basics, including a detailed guide to building your first project. I'll put links in the description and the card above. Beginners often start with one of these boards, an Arduino Uno, or something very similar. It has labeled I/O pins along the edges and female headers so you can easily plug wires into it. It runs at 5 volts, which is conveniently the same voltage as the USB ports on your computer, your charging brick, and USB battery pack. This board is designed for beginners, and it shows. You don't have to do any soldering to connect or disconnect your components, and everything has enough space around it to fit your fingers and to read the reasonably sized labels. The Uno R3 has an 8-bit processor, the Atmega 328, and you can program it using the Arduino software. Using the Uno as a starting point for comparison, we can start to change the properties one at a time, either the features on board, the form factor, or both. These days, there isn't a huge price difference if we speed up the processor to 32 bits, and that's why there are so many 32-bit boards available using the ARM Cortex-M0 microcontroller. For example, my favorite SAMD21 board is the Gemma M0 from Adafruit, and my favorite RP2040 board is the Xiao RP2040 from Seed Studio. These faster boards can run Arduino, but also a flavor of Python. If you want to code in Python or use one of the kid-friendly blocks code environments like MakeCode, that's a good reason to pick a 32-bit microcontroller for your project. The next big category of microcontrollers is SoCs, which stands for System on Chip. These include boards using the ESP32, ESP8266, NRF52, and other familiar names you might recognize. A system-on-chip device is engineered to take care of a special feature, often wireless of some sort, while letting you run your own code too, all in one package. All the ones I mentioned and show here also happen to be 32-bit microcontrollers, though the term SoC doesn't refer to the processor speed. My best advice is to match up the features and requirements of your project, as well as your abilities, with those of your board. Don't pick a microcontroller with extra functionality you don't need, but consider how your project needs might evolve in the future and at what point you might need to graduate to a bigger and/or more powerful board. There is no way to compare all of the available boards out there, but the Make Boards guide comes in close. In addition to the print and PDF version, which I'll link below, there is a handy site that lets you compare 2 boards side by side. And it has a big database of popular microcontroller boards across brands. If you're not finding what you're looking for, maybe you actually want a single board computer. I've got a whole separate video about how they're different from microcontrollers, so check that out if you want to learn more. The best way to get good at choosing a brain for your project is to practice. So using some of my past projects as examples, now I'll demonstrate some microcontroller selection in action. For my prop replica computer book from Inspector Gadget, I needed to host a lot of buttons as digital inputs. A bunch of those were illuminated buttons, so each of those LEDs needs its own digital output. An Arduino Uno has 14 digital I/O pins, not enough, so I could have added some shift registers or upgrade to an Arduino Mega, which has 54 digital I/O pins. Remember the iron triangle, which weighs against one another the opposing forces of speed, quality, and cost. You can have 2, but not all 3. So using the Mega was the fast and good solution. Using shift registers would cost the extra time to change up my wiring and the code to use them, but they are inexpensive, so that's the cheap solution. And how fast and good it is depends on your skill level. For my LED beaded curtain, I wanted to use a platform, somebody else's software, to control a big LED grid. This is a solved problem, and I might as well start with a leg up from folks who've thought about this before me instead of reinventing the wheel. So rather than investigating the specs of specific boards, I browsed community projects and talked to my knowledgeable friends and discovered a couple projects, WLED and Pixel Blaze, that are doing just that. Both consist of firmware for your microcontroller and a web or app control interface. WLED can run on a bunch of different ESP8266 and ESP32 boards detailed on its website, while Pixel Blaze sells its own proprietary hardware. This example shows that wanting to use a particularly cool platform is a totally acceptable reason to choose a particular microcontroller. Take a look at my LED painting project. I needed a microcontroller that was shorter than the thickness of my frame, easily able to connect with permanent soldered connections, and that could drive NeoPixels. There are lots of boards that satisfy this small list of requirements, but I also already had this Arduino Micro in my stash, which is another perfectly acceptable reason to choose a particular microcontroller. I also used only what I had on hand for my LED poles project, which mostly happened to be the classic Uno shape. This was not the absolute best board for the project, but in this case, I was optimizing for the fastest and cheapest options available to me, which was no longer that micro because I had already put it in my painting. For my LED Mermaid hair project, I wanted something small enough to clip into my hair with a sturdy USB-C port for connecting my battery pack, and that could also drive my fixed address pixel LEDs. The Xiao RP2040 board is one of the least expensive options that satisfies these requirements, though it runs at 3 volts, so it's technically at the edge of compatibility since the pixels really want 5 volts, but they'll also work at 3 volts in this case. If I wanted to run this same project with a LiPoly battery instead, I might go for a Gemma M0, which already has a port for one on board, and a handy on-off switch. The Gemma M0 is also the board I recommend my students use for their LED Halloween costumes. It doesn't give you access to very many I/O pins, but it's perfect for soldering beginners because the few pins that are there are far apart with big pads that are hard to mess up. I hope these examples help you understand how to put the concepts into practice. I've put some links to resources in the description. Leave your advice about selecting the microcontroller in the comments so we can all learn together. Check out the playlist with the rest of the series and subscribe so you don't miss the next one.